Okay, students, thus far you have seen a video of my lecture on the topic of thermochemistry, and we arrived at the definition of what we call the first law of thermodynamics. What we would like to do now is to practice with that to see how it works. This is an example taken from the textbook. If you want to just simply read the textbook and you're satisfied with the text explanation, then you're free to skip this video here, but sometimes students like to be walked through things directly. So what we're going to do is we're going to watch this example here and follow it. And what we have here is we're going to play some pool. And in our first example, what we're going to do is we are going to take a cue ball and hit it over here with a certain force. And as we know, a force applied on a mass causes it to move, and so it acquires a kinetic energy. Now, what we're going to do here is, in this analogy, we're going to assume that we are working on a smooth surface. Smooth surface, so the felt there on the table is very smooth. And what is happening now is the ball is traveling in this direction. And as it travels, it loses some heat, some energy in the form of heat as it experiences friction over the surface of the table. And it tells us here that the amount of energy that is released in the form of heat is 0.5 joules. As the ball arrives to the other side, it collides with a ball that was stationary. And as we know, the idea is for the cue ball to move that ball. So this ball now is going to now start moving. Let's assume, for the sake of this example, that all of the energy that the cue ball was bringing, which was at this point 5 minus 0.5, which is 4.5 joules, all of that energy is transferred to this purple ball here, and therefore the cue ball ends up stationary. So I'm going to go here and say that at this point it is stationary. So let's maybe put some numbers here so we can follow along. So number one, we applied a force which caused the cue ball to begin moving. In the process, it lost energy through friction to the surface of the table in the form of heat. It arrived at this other ball where there was a collision that caused that ball to start moving and the cue ball to now become stationary. Let me move this out over here so you can see it better. Okay, so there we go. Notice that at the moment we're assuming that the cue ball transferred all the energy it was bringing to the purple ball, and that was a residue of 4.5 joules. Now, let's do some energy calculations. First of all, remember that the energy itself is a property of the state. So in other words, a change in energy would be the final energy minus the initial energy of the cue ball. Now, at the end, we said that according to item here, number 6, which you can barely see here, the cue ball ended up stationary. In other words, it had no energy at all. And we said that it started with an initial kinetic energy of 5.0 joules. That's the total energy units. So we do the math and we get negative 5.0 joules. Remember, delta E, because it's final minus initial, can be either positive or it can be negative. Now let's look at the components of this change of energy. One of them was the heat. Now remember, heat is not a property that we can measure in a particular state. Heat is energy that is evolved or transferred during a process. In this case, we would say that heat would be the kinetic energy that was transferred to the surface of the table. And we said that that was 0.5 joules. Now remember, because this is energy that goes from the ball to the surface, in other words, from the system to the surroundings, it would have a negative sign, and we said it was 0.5 joules. The other component would be work. Once more, we say that work is energy transferred during a process. And remember that work means energy used to move things around. In this case, the energy transferred by the cue ball when it hit the purple ball caused the purple ball to move, right? And we would say this is the kinetic energy transferred to the purple ball. Once more, sorry about my poor handwriting. And we would say, again, this is energy that goes from the system into the surroundings. In other words, it's kind of like energy lost. So it has a negative sign. And this would have been the residue, which was 4.5 joules. So work is minus 4.5 joules. Now, according to the first law, the change in energy should be equal to whatever energy was transferred in the form of heat plus whatever energy was transferred in the form of work. So in this case, that would be minus 0.5 minus, because the work is negative, 4.5, and the units are joules. And as you can see, let me move this a little bit here. This brings us to a total of minus 5.0 joules. That would be the delta E if we calculate it on the basis of the first law. But notice that that number we just got there is exactly what we had here from simply looking at the initial and the final states of energy in our system. And as we can see, in this case, the first law of thermodynamics is obeyed. In this second example, we are going to do a similar experiment with just one difference. Notice that, once more, we are going to apply an initial kinetic energy by applying a force, as we said before. And you can see that it is 5.0 joules. The cue ball is going to move with a certain amount of kinetic energy at that point, 5.0 joules. But this time what we're saying is that our cue ball is going to travel over a rough surface. This is not a high quality felt. And so as the cue ball travels, you can see that it loses energy to the surface, but because there's more friction, the new value for the heat loss is 3.0 joules. That means that when it collides with the purple ball, it's bringing only 5 minus 3, 2.0 joules at that point. So let's repeat our calculations that we did before. First of all, let's start out with delta E. Again, this is final energy. And don't forget, as in every other thermodynamic treatment, we define our system, which in this case is the cue ball. And the surface of the table and the cue ball and the purple ball are both part of the surroundings. So the final energy was 0 again, because it ended up stationary, and it started out with an input of 5.0, and this is all in joules, for a total of minus 5.0 joules. Notice that this is the same value that we got before. Even though the path was different. In other words, in this case, the ball traveled over a rough surface. What matters with changes of energy is what is the final and the initial state. And that is the same for both the experiment here with the rough surface as it was with the first one with the smooth surface. Let's now calculate the other amount. Let's talk about the heat. Again, this is again the kinetic energy transferred to the surface. Again, this is different because this is a different quote-unquote path. And in this case, we saw that it was 3.0 joules. But remember, because it is energy transferred out of the system into the surroundings, it is considered a quote-unquote loss of energy and therefore has a negative sign. In this case, now the work would be the kinetic energy transferred to the purple ball, right? We're assuming once more that all of the energy that the cue ball brought is transferred to the purple ball, and so the white ball ends up at a perfect stationary state. That's an assumption we're making. And in this case, we know that it was 2.0 joules. Once more, because this is energy going from the system into the surroundings, it has a negative sign. So let's see what the first law of thermodynamics is going to tell us when we calculate, the delta E. So according to the first law, this would be Q plus W, right? This is what the first law tells us. And that would be minus 3.0 minus 2.0, and this is joules. Q is the heat, W is the work, they're both negative, and this gives us a total again of minus 5.0 joules. Notice once more, as before, that the delta E calculated using the first law is the same as the one calculated from the definition of delta E. Again, we see that delta E, being a property of state, is the same regardless of how the cue ball arrived from a stationary position here to a stationary position over there. However, in the process, the energy change happened in different ways. In this case, more of the energy change was due to heat loss, and therefore there was less energy available for work. I'd like to take a few moments to make sure that we have certain concepts clear in terms of specifically the signs of heat and work. So remember, the first thing we do is we define what is our system, right? So our system could be a cue ball being hit across a table, pool table. It could be a rocket being launched from a surface on the earth, from a base. It could be a chemical reaction happening in a test tube or in a container. Once we define the system, of course, we have everything else around it is the surroundings. And many times, what we observe is actually not the change in the system, but the change in the surroundings. We will see that when we study the topic of calorimetry, in other words, the measurement of energy changes during chemical reactions. What we said is that there are two ways in which energy can be exchanged between the system and the surroundings. One of them is heat, which is an exchange of thermal energy, and another one is work, which is either the system pushing out and moving items in the surroundings or vice versa. Now, let's say that I have a change where energy goes from the system into the surroundings. Any change in energy where there is a flow from the system to the surroundings is considered, quote unquote, a loss. I'm going to write it here. and it will have a negative sign. So whether we're measuring delta E, Q, or W, all of those will be negatives. Notice that in the case of work, it's a little hard to envision, but the idea here is that the system is doing work against the surroundings. It's moving surroundings out of the way. That requires energy to be spent, quote unquote, into performing that work, and that's what we call W a negative. That's what we assign work, a negative value. Now, if any energy goes from the surroundings into the system, what we would say, therefore, is that the system has experienced a gain. Sorry for my lousy handwriting here. And so when there is a gain, we have a positive sign. So whether it's delta E, Q, or W, all of those are now going to have a positive sign. Notice, again, for work, what does this mean? Well, it means that the surroundings are doing work against the system. Energy is being used by the surroundings to move the system. Therefore, the system is gaining energy in the sense that it has work being performed on it, and therefore that's why work is positive. Don't forget, according to the first law, regardless of what the process is, the total energy change of the system will be composed of whatever heat transactions happen plus whatever work transactions happen. And the positive and negative signs of each should all combine to give us always the same delta E as long as the initial and final states of the system are the same. In the previous examples, we used a pool table and a cue ball traveling over the surface of that table to illustrate the first law. Now, this is a chemistry class, and what we really want to study is chemical reactions. So let's start looking at how we're going to approach that. You're familiar with this type of diagram where we plot the energy of a process against the progress of that process. Let's say that in this case, what we're tracking is a chemical reaction. So we start with reactants and you end up with what? Products, that's right. So for the sake of illustration, let's say that the energy of the products is down here. Once more, we apply the rule that the delta E, the change in energy for this process, would be final minus initial. In this case, the final state would be the energy of the products, and the initial state would be the energy of the reactants, correct? And I am abbreviating here to save some space. But in this case, notice that according to the chart, the energy of the products is lower than the energy of the reactants. So that means that when I calculate delta E, I'm going to have a negative value. All right, so this is a process where energy is lost, where there is a negative delta E. Now the question is, how do I measure this? How do I know this? And I'm talking now practically. Because the reality is, if you think about it, if a chemical reaction is basically atoms and molecules, colliding with each other and making changes in the types of connections that they have, it would be very difficult for me to actually visualize that. And so what we do is we remember that in a process, there is a law called the conservation of energy, right? And the conservation of energy tells us that during any chemical change, the delta E of the system, which in our case is the chemical reaction, plus the change that accompanies that reaction, but in the surroundings, should add up to 0. That's correct, because energy is conserved. There is no net gain or loss of energy in the universe. So that means that delta E of my system should be equal in magnitude but opposite in sign to the change, whatever it is, that happens in the surroundings. And this is very important for us because essentially this is what we observe. Or let's say this is what we measure. In other words, I don't really measure the change in energy of the system. I calculate it based on the measurements I make on the surroundings. Let me give you a sketch of an example. Let's say that I have my chemical reaction happening in water inside a kind of a container. And I'm going to make that container insulated so that essentially there's no energy exchange between the interior and the exterior. So no energy exchange between inside or the outside of my container. Notice that in this case, in this reaction, we said that the energy dropped as the reaction progressed from the reactants to energy. So in other words, delta E of my system, all I know is that it is negative. There was energy, let's say, lost. But did it get lost? No. Not really. Energy was transferred to the surroundings. That's what delta E negative means. It looks like a loss with respect to the system, but what it really is a transfer. Now, in this case, the surroundings are water. So what we're going to see is that when that happens, we observe that the temperature of water increases. That is our observation. Notice that we said we observe delta E in the surroundings. In this case, what we observe is the temperature of the water increases. And that is what we do. Now, we're going to need some equations and some formulas to convert that temperature change into an actual amount of energy. But once we know and we can calculate what was the energy change for the water, we can go back to our premise here and say that, well, now that I know what was the energy change in my surroundings, I can figure out what is the energy change for my system, and specifically in this case, for this chemical reaction. So we're going to learn more about this in our next set of lectures. Thank you. Enjoy.